Okay, so I've asked you to identify three of the five quantities, V naught, V of A, delta X, delta T, in each of these situations. You did quite well with this. Then I asked, what's the first equation you would use to solve the motion? Well, most of you didn't remember all the equations. I don't remember if anybody remembers them all. Most of you had a couple of them, maybe not as many as three, but nobody had all of them, I don't think. But I wasn't totally looking for that. That's no surprise today, but after this, you should have done enough problems with these equations. They're second nature to me. Okay. And you have better insight into how they're used. And then we also want to talk about the idea that you want to then make sense of your solution. You can do this mechanically and just follow the algorithms, get all the numbers and all the right answers without understanding anything that you did, except mechanics. That's not physics. It's a step. It's important. Okay. And it's a good skill to have, but you want to build on it by understanding what you're doing. Okay. Now I'll talk about that as we go on. Okay. Oh, okay. I start from rest and accelerate through 100 meters, accelerating at 2.3 meters per second squared. Now there'll be a little slide. You just kind of indicate these quantities in here, then I'll kind of listen. Okay, so let's see. What do you know? 100 meters. Well, that's going to be your delta X. 2.3 meters per second squared. That's the word acceleration. It must be acceleration. Okay. And we need a third one. I don't see any numbers. Okay, what do? Well, everybody pretty much knew because we kind of used it last time. Starting from rest, you know that now V naught. Okay. That is V naught, see, which makes everything very simple. Okay. Now we'll come back to answering the second question. Let's just go ahead and identify the quantities for the others. Okay. Start out at 4 meters per second, end up at 1 meter per second, travel 40 meters. Well, that should be pretty obvious. I think everybody pretty much got it, but you didn't. This is what you start at. This is V naught, 4 meters per second. Okay. This is VF, 1 meter per second. Now your book uses equations with V in them and not VF. And it uses some extraneous symbols, and you don't have this, quite have this neat little package of 5 parameters. Okay. And you don't have the 4 equations such that whichever 3 parameters you know, you can find an equation to solve it for. Maybe 2 equations, okay? So it's not quite as simple. I'm going to make it as simple as possible, and then we're going to work on understanding all the indices. Okay, now, you travel 40 meters, there's your delta X. I know 3 things, right? Now, throw a toss a ball upward at 12 meters per second. Well, that would be my V naught. Okay. I've got 2 meters below the point where I released it. So that would be my what? Well, that's my delta X. Delta X is from start to finish. It doesn't matter that you follow a path that's longer than your delta X. Delta X is just your displacement from start to finish, okay? So delta X is 2 meters below. So I'm going to circle the 2 meters, and I'm going to circle the below. There's your delta X. Okay. Now, what else do you know? Yep, that was a good gesture. Okay. Okay, so what I asked for, okay, well, somebody took that 75-pound weight I had back there, held it up and dropped it under his feet. Okay. That was a wonderful demonstration. It got everybody's attention. Rescue squad got here, took them off. Okay, so, no, actually, but somebody just dropped a pen on your table. It was a good demonstration. Not that easy to lift that 75-pound block of iron over your head. Okay, let's look strong enough to do if they have the flexibility in the shoulders, not that much. Okay. Strong begins with being able to put your own weight over your head. And pretty much everybody can do that if they work at it. Takes a little work and it's dangerous. So maybe you don't want to do it. Okay, well, all the digressions aside, that indicated that it's the acceleration of gravity. Okay, and I think everybody picked up on that. Then I asked what the acceleration of gravity was. Somebody said 9.8 meters per second squared. I said, yeah, that's more accurate. But you're gonna see me using 10 a lot. And then doing a 2 or 4% correction depending on how I'm calculating. Okay. That's usually a 2% correction. Okay, so now we can write out quantities. Okay, so let's number these 1, 2, and 3. And I said 3 had a twist. There are a couple of twists in it. One is you got to know what the acceleration of gravity is, note that that is your acceleration. Okay. So the first one, d naught equals 0, delta x equals 100 meters, a equals 2.3 meters per second squared. Now I'm going to write out the equations. First equation, that's in, try to get them in the order that I listed them. All this equation says is that your displacement is your average velocity times your time interval. It's multiplying velocity by the time. Get how far, okay? Although these are vector quantities, they can be negative. So talk about displacement instead of distance, okay? Displacement can be negative. Second equation. Okay. All this says is start out at some velocity, and this is how much your velocity changes, because that's what acceleration times the time interval gives you. Okay. So there's trivial meanings to both of these equations if you understand what acceleration and displacement and velocity are. The third equation, this is the one you get. And of course, this equation also comes immediately if you integrate a constant acceleration with respect to time. We did that on the first day. Maybe just secondly. But we did that early, and you should understand how that works. Third equation then comes just integrating this with respect to time. And you get okay. And the delta x comes from the constant term. Delta. Okay. Fourth equation. You can best understand this equation by just understanding what you do to these two equations. If you take the simultaneous equations and eliminate your delta t. So it pops right up. And with there in front of you, smiling at you. Okay. This equation leads us directly in a limited case, but still a pretty broad case, to the whole concept of energy. and work. Okay? This leads us to the whole concept of impulse and momentum. I just want to get those words out in front of you, so they should echo a little bit in your brain. Can you understand that they come directly from these equations? First, we need Newton's second law. Okay, and we're not there yet. All right, we got the four equations. Which equation could you use? Okay, well, we check them out. This is the first equation where, let's say we know delta x, we know v naught, but we don't know vf or delta t, do we? Now, if we find vf or delta t, that'd be a convenient equation to use to find whichever one we haven't found, right? Okay, second equation. We don't know the final velocity. We do know the initial velocity. We know the acceleration. Oh, doggone it, we don't know the time either. So we don't know vf or delta t, so we can't use it. Let's go to each one of these longer equations. Okay, so what's this equation have? Got a delta x. Okay, we're good there. We've got a v naught. We're good there. It's got an a. We're good there. You got delta t, but you got it in two terms, one of which is squared. This equation is quadratic in delta t. And it's delta t that we don't know. It can be a little confusing solving a quadratic equation at this point. In a week, it won't be because you're going to have to. Okay? But right now, if you can find another equation to use it. Okay? So you don't have to solve a quadratic for delta t. It's also messy. Well, fortunately, this equation also has v naught and delta x and a. Okay? It allows you to solve directly for vf. Right? So I could say here we could use number 3 or number 4. Number 3 to find delta t, right? Let's say could use it to find delta t, but it's quadratic in delta t, which we might like to avoid. If possible. Number 4 to find vf. But of course, it's quadratic in vf, isn't it? Because you got a vf squared. Quadratic in vf, but it's simply the number 3. And that's the thing that comes out with a quadratic. To solve this one, you'd have to use a quadratic formula. So you get the negative b plus or minus square root of b squared minus 4ac all over 2a, right? You have a plus or minus, and you got to decide which one to use. Okay? That can be tricky. Even for this problem, it could be a little bit tricky. And it turns out that what you do is you use one of the solutions and discard the other. Or maybe use both, because maybe both are possible. Solve this one, well, you got to plug numbers in these things, then you're going to get the square of VF, and your solution is going to be VF equals plus or minus something, right? It's not a negative B plus or minus something over something else. Okay, it's just a plus or minus something, and it's easy to decide which one makes sense. And sometimes both make sense. Okay. So just kind of wonder, there's no real subtlety in this, except that kind of this choice between which quadratic to use, and the fact that you do get a plus or minus, whichever one of these you use. And in this case, one of them is going to necessarily make sense. Okay. All right. Now that's mechanics, though. They can just check through all four equations. Pretty soon you get a feel for which equations that mesh up with which choices vary. Okay. Right now, you kind of do it. Checklist stuff. Okay. Well, number two. What do we have? We got V naught. 4 meters per second. VF equals 40 meters. And delta X, sorry, that's 1 meter per second. And delta X is 40 meters. I did say make sure you put the units in these things. Don't leave the units off. And when you use the equations, do the unit calculations. Because if you're doing something wrong and you're likely to do some wrong things, the units don't work out. And you know now that something's haywire and you go back to fix it. You do the dimensional analysis and you do just using the units constitutes a dimensional analysis, okay? So which equation? P naught VF delta X. Bingo. Okay, that's really easy. Matter of fact, you don't even need an equation. If acceleration is uniform, you can just average these two, you get 2.5 meters per second. Okay. That's your average velocity for 40 meters. So you divide 40 meters by the 2.5 meters per second, and you get 16 seconds. Okay. Make sense? So if you need an equation for that, you don't. But as an exercise, it's okay to use the equation, but then you want to think, you really need that equation? Okay. Like in this one, if you get VF, then you know V naught and VF, so you get the average velocity. Divide that into delta X, and you get your time, and you don't have to use an equation, okay? So you should be able to do that, but you should be able to do it just confining yourself to the equations, and then using a little common sense, and you can easily figure out what you know, the acceleration or the average velocity for the change. Okay. So anyhow, what equation? We got V naught, VF, out there, acceleration. Okay, you got acceleration here, you got acceleration here. And you know 4 out of the box, you know either of these equations is going to work. It's probably easier. This is not hard. The quadratic and delta t doesn't hurt because you're not trying to find delta t. Okay. Well, I think this is making sense to you from what I saw you do. Okay. You had a really good start on this. So number 3, it's a little trickier to get this stuff, okay? V naught, of course, is 12 meters per second. And delta X is 2 meters. Oh, it's not really 2 meters. It's 2 meters below, which means 2 meters down, isn't it? Okay. So you're tossing the ball upward, but the displacement is downward. You better choose your positive direction. Okay. So it can't be this, because these will both be in the same direction. And since this is upward, they have to both be upward, and this isn't upward. Okay. There's a contradiction there. So you choose. Now you could let up be the positive direction. Okay. Now, if up is the positive direction, then what is the acceleration of gravity on screen? Okay, yeah, at this point, you know, These can't both be right. So what you have to do is choose your axis. Choose your coordinate system. In this case, it's just a one-dimensional coordinate system. It's a vertical axis, right? You want it to be positive in the upward direction or in the downward direction. Now you kind of think of upward as being positive. Of course, if you choose upward as positive, your gravitational acceleration is downward and that's negative, right? So you want to consider that. If you choose upward as positive, gravitation will be negative, and of course, that's only your delta x. Because your delta x is down. Okay? So you'd have two negative quantities. And it might be mathematically easier. You might understand it better. Probably not, but you might. If you let downward be positive, just reorient your standard thinking. Okay? Then you only have one negative quantity, which is negative 12 meters per second, because it's up and down is positive, right? So you always have a choice of your coordinate system in one dimension. Okay. Well, how many want up to be positive and how many want down to be positive? This for up, this for down. Well, it's kind of close with the ups happening. Okay. So up is positive, so now x, delta x is negative 2 centimeters. And your acceleration is, I'm going to use 10 meters per second squared, but that's going to be negative because it's down. Understand that? Because it's a pitfall to not explicitly declare what your coordinate system is. Now, if all the quantities you have are in the same direction, then it's kind of implicit. But if some quantities are in opposite directions, you got to make a choice. And again, if it's chosen downward as positive, you'd have two positive quantities here instead of two negative quantities. But of course, you have the negative. Since we're more comfortable, most of us, with upward being positive, that's a choice most people make. But you should be able to work it out both ways and see what it makes. If you ever want to understand general relativity, this is a good place to start. We did the option coordinate system, and you don't know what I mean by that. I just foreshadowing is something you probably never do. Not much engineering makes heavy use of general relativity. Although if you're generator, if you're doing the GPS system, it does. The general relativity is really, really fun. Okay. That's the reality. We have this, so what equation we're going to use? You know, V naught, delta x, and A. Let's see. First equation got V naught and delta x. It doesn't have VF or delta T, just has A. Second equation has V naught and A, but it doesn't have delta x. Okay. And again, by putting these two equations, you get these two, but not going to work on that right now. Okay. So this one has delta x and it has A. It has delta T, but it has V naught. Look at that. This one appears to have everything we need except delta T, right? But again, we'd end up solving for delta T, right? So number 3 could work. Number 4. Probably better choice. We got V naught, we got delta X, and we got A. And again, we're going to be able to find VF. Now, whichever you solve for, delta t or VF, and it is possible to solve this with delta t. You got to keep your wits about you, and you don't want to challenge your wits too much early in the course. Big challenge from next week. Okay? Whichever one of these you know, you got a wealth of equations. Any of the other equations, you probably get at least two. Okay? I'll say, then you got plenty of options to find that fifth error. You got four of them. You're almost. Okay. Well, the easiest solve is first, but we started off with an easy one. So number one. Okay, problem one. Got numbers to solve, plug in for each of these. Solve the equation very easily. Plus or minus the square root of P naught plus 2a double f. Okay, and we've listed B naught and all that. So B naught is 0 plus 2 times 2.3 meters per second squared. Once see writing the units right there in the equation, using them at every step, and actually calculating the units. Okay. Your own benefit. Your delta x is 100 meters. What do you get if you multiply meters per second squared by meters? Well, you get meters squared per second squared, right? And you got 460 meters squared per second squared. Okay, now, what's the square of 460? It's pretty close to 21.5. And you, the square root of meters squared over second squared is meters per second. That's plus or minus 21.5 meters per second. Okay. That could be off by 10. Nothing about finding on that. Now, wait a minute. Yeah, it's probably. Okay. Plus and minus both work. Well, if it's plus 24 meters per second, then that's consistent with a positive acceleration from rest, right? A negative 21 meters per second doesn't really seem to work well, does it? Because once you've accelerated at 2.3 meters per second to the 100-meter mark. If you continue accelerating at 2.3 meters per second squared in the positive direction, you ain't coming back. Okay, and you have to go past and come back somehow in order for that negative to work. Does that make sense? Does it make sense? If the negative doesn't make sense, and sometimes the negative does make sense. Okay, well, you got to think about that. Discard the negative solution, but if you do, you better be sure that it actually doesn't work. Okay? Okay, well, now we know V naught and BF, so we can find the average velocity, right? And once we have the average velocity, we know the displacement, so we could easily find the time without having to use a formula, right? So I'll just put in parentheses. Not sure why I haven't it up there and wrote meter per second, but it's in the denominator. You divide meter by meter per second. It's like multiplying meter by second over meter and gives you seconds. So that's going to be about 9.8 seconds, which has nothing to do with acceleration of gravity. Just really have to come out and then plan it that way. Okay. Makes sense? So you could do this, but we're going to use equations. We're going to get used to using equations. I say, I don't say what to do after that, do I? Okay, well, I'll end it on here. Then say what you did next. Well, since you have two choices. I'll say number 4 is used. Then we're going to use number 1 to get delta t. We'll have the if number 3 was used, you'd have delta t, and you could find delta x from equation. Either way, you can use it. So there's our equation. We want to find delta t. Solve for delta t. You just multiply by the reciprocal of VF plus V naught over 2, then you get delta x times 2 of 2 delta x over VF plus V naught. That's going to be 2 times 100 meters over 21.4 meters per second plus 0 meters per second. Equals about 9.8 seconds. Now, using equation 1, I just did that mechanically. I didn't think about what it meant, did I? But what's it saying? This VF plus V naught over 2 is your average velocity if the acceleration is uniform, right? So this just says delta x is average velocity times delta t. So we can divide delta x by the average velocity to get delta t, but we already knew that. And that's what we want to think, even if we just mechanically use the formulas, we want to go back and think, well, yeah, this really had a meaning. This 2 over VF plus V naught is the same as dividing by the average velocity. Identify as much of that stuff as you can. You get better and better at doing the problems, okay? Better at thinking, sharpens your thinking, has all kinds of benefits. All right, well, that's kind of straightforward. Okay, second. You know, V naught, VF, delta X. That number one gives delta T. Number one is again. So that's 2 times what? Delta X is 40 meters. V naught is 4 meters per second plus 1 meter per second. That's going to be 80 meters over 5 meters per second, which is 16 meters times second over meter, which is 16 seconds. And I didn't do that meter times second over meter thing. And I skipped the step where I divided the 5 into the 80. So I was only worried about the units. Meters divided by meters per second is meters times seconds over meters, right? Make sure you understand that out. It might be a little confusing, okay? My algebra was really strong when I started. I've been with this course. And I had to think, make sure I didn't do what might have seemed obvious. Wasn't right. I knew how to resolve it. So I'm not making mistakes in that. It's easy. Screw ups. Make sure you're really aware of all the algebra. Always meters per second, meters per second squared. Since meters per second is divided by seconds, which means it's multiplied, meters per second is multiplied by reciprocal second. That gives you second squared denominator. You need to know this. And they're not all crystal clear. Everybody, by the way. All right. Anyhow. It's easy to just find V bar and divide your 2.5 meters per second into 80 meters to get 16 seconds. Okay. It would be easier, quicker, and you would be displaying a better knowledge of physics as opposed to rote use of equations. They should be able to do both. If you're using this equation, think what it means. Like, yeah, I could have done this, and when I get used to using these equations, I'm probably going to do it that way. Okay. Some combination of direct reasoning. I call this direct reasoning. You know what velocity means? Average velocity means. Then you know this. Okay. And you don't really need that equation. Okay. Well, anyhow, then still need the acceleration. Well, this equation didn't involve acceleration. All the others do. You can use any of these. But This linear equation, here's a sentence. A is VF minus V naught over delta T. And that right away, oh, God, yeah, definition of average acceleration, right? So you didn't need to actually find an equation. Could have just used the definition of average acceleration. No VF, V naught, velocity changed by 3 meters per second. Okay. And did that in 16 seconds. So it's going to be 3/16 of a meter per second squared. Okay. You want to think about these connections because they're not going to be obvious to you right away. But you keep coming back and recognizing when something reduces just down to the definition of average velocity or average acceleration, or where you could just use the average velocity or average acceleration without having to get fancy with an equation, right? Then you have a deeper knowledge. You can still use the equations. If your brain isn't working and you just got to plug numbers into the equation, maybe on a little code or something, your brain just doesn't work well. At least mine didn't. Okay. The last equation, the last problem. Where's the information? Online. Okay. You know, V naught, delta X, and A. Okay, so you got V naught, delta X, and A here. You use a third equation, but it's quadratic, right? Fourth equation is also quadratic, but it's a little more obvious what to do with the plus and minus that you get. Okay, so go to the fourth equation. Okay, now, V naught squared is 12 meters per second. So let's see. What should be able to see it? Probably gonna know right so big, but I still run out of room. But I'm gonna make a real effort to make that sum. Okay, so we have again. Square root of 12 meters per second squared. Acceleration is -10 meters per second squared. Delta X is -2 meters. That would be 2, I think it's great. It'll be 144. It's going to multiply out to 400. So you're going to have 544 meters per second squared times meters is meters squared per second squared. All the units are consistent. We can add them. Okay, 25 squared is, oh, wait, 644. Okay, 23 squared is 529. 1.4 squared is 576. It's about a 0.4. So I'm going to say plus or minus 23.4 meters per second. Okay. Now, again, in this case, ball was thrown up and it ends up down. It's obvious that its final velocity is going to be downward, right? Downward isn't automatically negative. It depends on your choice of the coordinate system. But we chose to use upward. You all chose, you put it. Okay. It's like 43 in favor of something. And you might want to work it out with downward because numbers are simple and the same as they are here, but the signs are different. What happens when you change those signs? Be worth thinking about if you have time and interest. Okay. Anyhow, it's obvious that VF is downward. Okay, now. You can average initial final velocities, right? And you get, what is that? Negative 11.4 on 5.7 meters per second. That makes sense? Well, toss this piece of chalk up, it falls down. Okay. Spend more time going down than it did going up. Ended up faster than it did when it started, but in an opposite direction. So it makes sense that you have this sign of the negative, right? But you want to think about that. You know, back before we all were born, I think any of you all would love to do a lot of that happen. Back sometimes in the 90s. And some of you might go back that far. I don't know, it's hard to judge ages. Some of you look pretty old now. Seriously, big expensive space probe was sent to Mars. Okay. And it got there and everything was looking really good and it crashed right into Mars and, you know, there's a piece of it bigger than a grain of sand left. Okay. Kind of like that, but it was going really fast. Why? Because somebody put the mass of the thing in pounds rather than kilograms. And the calculation that it did to determine how to slow down, it's much, as much, not enough. Okay, and multi-billion dollars. Okay, got to use shoes, folks. Engineers have it, notorious have it, for never writing degrees when they mean degrees. And you can't tell whether they're talking about degrees or radians, except if the number is really big. It's probably degrees, but it might be radians because radians can get big too. Okay. And you know, not writing out units and we're just writing out the numbers and taking them as they are. And if they got a wrong variable in there, they never find out. Okay, and their spacecraft blows up again. So I don't want y'all blowing up spacecrafts, okay? They're expensive. Also, they're probably not good for your career if you're responsible for it. Okay, the engineer's got to be precise, and part of being precise is not just the numbers, it's the meanings and the units, so you really know what you did. Now, you're always free to ask Mr. Hale about anything that I say. Take his word over mine about engineering. Okay. He might disagree with me on some of that, and if he does, let me know. I don't mind getting corrected. Yeah, you might fail, but I don't mind. I'm fine with that. Just trying to get to the truth here. Okay, so anyhow, we got this. Okay, now. You got delta x over v bar, but v bar is negative. Won't that give you negative time? Well, what if that delta x is positive, the delta x is negative? That's your displacement. And now this doesn't make any sense at all. It's approximately 0.3 some seconds, and it certainly takes more than 0.3 seconds. Go up and down. Okay. So I'm going to leave that as kind of a district. Yeah, check back, make sure that final velocity is really positive, that the average is really correct, and this is consistent with the sign of your acceleration. Okay. I'll put some stuff in the on the assignments page about lab. I do want you to have the chapter 2 problems with you. So they were due Friday. Okay, some were due today, I think I said. But I'll wait till Friday. Maybe if you got them today and let me have them, that's great. If you want to hang on to them until Friday, but if you only got one copy, you might want to keep it so you can reference and go get the rest of them. Okay, if you got them all done, you can have them now. Whatever. Okay, let you hang on to them until Friday if you wish. Yeah, give you a heads up on a couple other things. Make sure that you're pretty good with vectors. Because one thing we're going to talk about is vector velocity, that penny here versus vector velocity here, and the difference in those vector velocities. Okay, which leads you immediately to centripetal acceleration. Since the chapter is coming up, and what we're working on next week is on motion in 2 dimensions. This is motion in 2 dimensions, right? Now, it's an angular motion, and the angular motion is not really a 2-dimensional motion, but the motion of the penny is in 2 dimensions. The motion of any point of this thing is in 2 dimensions. Okay. So we're going to investigate a couple of things about the vectors that arise here. And we're also going to do some stuff with acceleration, relative accelerations. What do you do if you try to compare the velocity of 2 objects, like a cop sitting there by the side, you come by at 90 miles an hour. He accelerates 6 meters per second squared, which is feasible. Subtraction is really good, maybe even 7 or so. And how far do you go before he catches it? Now, if you accelerated 8 meters per second squared, he's never going to catch you, right? Until he calls in the helicopters with, the rockets and stuff. But those are interesting problems, and they get to what I wanted to get to today was the idea of these things as a function. Vehicle velocity is a function of time, position is a function of time. But we'll talk about that briefly on Friday. And you see it in the text. There are a couple of problems set that involve that. Okay, so try to get prepared, and then we'll try to bring it all together. Okay, very good. We're out of time, and y'all have places to go. Have a good weekend. No, I can't tell you that until Friday. Have a good rest of the week and I'll see you Friday.